Hello everyone, this is Roy PCB, your trusted PCB partner. Today our topic is the design of power and ground planes in 4-layer PCBs, as well as considerations for current paths and density. In previous lessons, we've already learned about the importance of ground and power planes in 4-layer boards. They provide signal return paths and are key to achieving impedance control and EMI management. Today, we will delve deeper into these planes, especially how to design their current paths and avoid excessive current density, which is crucial for ensuring power supply stability and system reliability. Next, let's look at the layer structure of a 4-layer board. Do you remember it? The top layer is the signal layer, L2 is the GND layer, L3 is the power layer, and the bottom layer is another signal layer. This is the hierarchical structure. What are the core functions of the power and ground planes in a 4-layer board? First, they serve as the primary impedance power distribution network. The GND and power planes together form the power supply and return network for all components on the board. They create a large area planar capacitor, providing much lower impedance than traces, which allows for more effective and stable noise absorption and stable voltage supply. Second, they act as signal reference planes. As we mentioned in previous videos, they provide a continuous and stable return path and reference for high-speed signals, which is fundamental for signal integrity and EMI control. Third, they help with heat dissipation. Large copper planes also facilitate the conduction and dissipation of heat generated by components. For example, in our circuit, it's a power supply board with relatively high power, so it requires a lot of space for heat dissipation. In this case, different planes can be used to conduct and dissipate heat. Current density is a hidden killer in PCB design. So what exactly is current density? Current density refers to the amount of current flowing through a unit cross-sectional area. In PCB copper foil, if the current is concentrated in a very small area, the current density will be very high. Current density is equal to the current divided by the cross-sectional area. For our PCB, the copper thickness is basically fixed. When we select and manufacture it, we can only choose a thickness of 1 ounce or 2 ounces, so the cross-sectional area mainly depends on the different widths. When the width is smaller, its cross-sectional area is also smaller, so the calculated current density will be higher. What are the dangers of excessive current density? The first is overheating. High current density can cause severe local heating of the copper wire, increase copper loss, and even burn out the trace or cause the copper to separate from the board. The design is not reasonable. You will often see traces being burned out, some local copper wires being burnt through, or even the PCB being scorched. These are all possible. The second issue is voltage drop. Even if there is no burning, high current density will increase the local resistance, resulting in a voltage drop. This causes the voltage received by components to be lower than their rated value, affecting their normal operation. For example, if the return path for large currents is too narrow, it can cause a local voltage rise on the ground plane, which affects the signal reference. Now, in this circuit, let's assume there is a large current at this position, and this area is very narrow, with large currents on both sides. In this region, when the current is high, it will generate heat, and the heat will cause the resistance of the copper foil to increase. As we've discussed in physics, the higher the temperature of a metal material, the greater its resistance. The greater the resistance, the faster the temperature rises, so this creates a vicious cycle. When there is resistance at this position and a sufficiently large current, even if both sides are ground, both are GND, a voltage difference will still be generated. This means the ground plane voltage becomes unbalanced, which will cause the reference voltages of components on both sides to deviate completely. Thirdly, reliability will decrease. Long-term operation at high temperatures will accelerate the aging of the PCB material and reduce the product's lifespan. So what is the current density of a plane layer? Although the area of the plane layer is much larger than that of traces, when the power or ground plane is split or when connecting high power devices, the current may be forced to concentrate in a narrow designated area, resulting in excessively high local current density. For this, we can refer to the bottom layer design. Although the bottom layer is a signal layer, all the components are placed on one side and there are basically no traces on the bottom layer, only two areas. One of these areas is separated by micro engraving and the rest is used as GND. If we look at it solely from this perspective, then this circuit has a problem. GND only exists after being separated by micro engraving, and only these two narrow areas connect both sides. If the current on both sides is too large, it will result in what we call high current density. This layer is the GND layer. Its network is GND and there are no separations. So on this layer, the integrity of the ground plane is maintained. So even if the underlying plastic layer does not meet our design specifications, this circuit is still fine. How do we design current paths to avoid excessive current density? To ensure the stability and reliability of the power ground plane, we need to actively guide the current path and avoid high current density. First, maintain the integrity of the plane. This is the core principle. The ground plane should be kept as intact and unsegmented as possible. If the power plane needs to be split, the dividing lines should be as wide as possible to avoid creating narrow planes. This is just what we mentioned earlier, maintaining its integrity on the L2 layer. Although there are narrow splits in the lower layers, overall, large current return paths. For high current and high power components, such as CPUs and power management chips, their power and ground should, as much as possible, be connected directly to the corresponding power or ground plane through short and thick vias. This ensures that the return current can quickly disperse into the ground plane. As we can see here, all the components are on the top layer. You can see that in every area with large currents, there are many vias placed next to the component pins to conduct current and dissipate heat. Third, avoid the antenna effect. When routing traces on the plane layer, although signal traces are not recommended, sometimes they are unavoidable. Or when making cutouts on the plane layer, make sure not to create a long, narrow strip that forces all the current to pass through a confined area. This can result in a highly visible increase in radiation. Both avoid hotspots. By arranging the layout of the first power layer, distribute high current paths evenly to prevent current from concentrating in specific areas and forming hotspots. Today, we learned about the core role of power and ground planes in four-layer boards, as well as the potential hazards caused by excessive current density. We emphasized avoiding high current density by maintaining plane integrity and optimizing high current paths. In the next lesson, we will focus on another important characteristic of the power plane, ripple suppression, and how to use the features of the power plane to reduce power supply noise. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.